Check it out now, y'all.
NanoHub U, online instruction.
So in this lecture, we'd like to explore some of the consequences of this electron spin that was discussed in the previous lecture. And in particular, what I like to emphasize is that the discovery of the electron spin meant that the wave functions, the eigenfunctions for the hydrogen atom, had to be rewritten. And that point I try to make here in this slide, where I take the eigenfunctions for the radial and the angular part of the electron in the hydrogen atom, right? I take those and I just simply multiply them now by a spin wave function chi, and the quantum numbers that describe the spin wave function are going to be given by this new quantum number m sub s, and m sub s is either going to be equal to plus 1/2 or minus 1/2 in order to describe whether the electron has a spin up or a spin down. So this spin gives rise to an intrinsic magnetic moment that's somehow associated with this spinning electron, and the new wave functions now for hydrogen require you to specify 4 quantum numbers instead of the original 3 that we've been discussing for the previous few weeks. The implications of this spin are really far-reaching, and we're actually going to spend the next few weeks of the course discussing the consequences of electron spin, and it shows up in a number of different areas that we'll discuss. One thing that it requires us to do, to be precise, is it requires us to be able to rewrite wave functions now in terms of possible values for the spin of the electron, in addition to the quantum numbers n, l, and m sub l that are given for the radial and angular eigenfunctions. So for instance, if you want to write a proper wave function for the ground state of an electron in the hydrogen atom, you have to allow for the possibility that that electron could either have a spin up or a spin down. The other quantum numbers are determined once I tell you that it's the ground state, because the ground state tells you that n is equal to 1, script l is equal to 0, m sub l is equal to 0, right? And ahead of time, we don't know whether the electron is spin up or spin down, so we have to include coefficients C1 and C2 to describe the relative probability that the electron is in the spin up state or the electron is in the spin down state. And if we can do an experiment that measures C1 and C2, then we can actually calculate the probability of finding the electron in the spin up or the spin down situation. Again, I would like to emphasize that these spin wave functions, at this point in the course, these things are just invented, and they're invented to solve 2 eigenvalue problems for spin, right? One is the square of the spin angular momentum, and the other is it's not an angular momentum, it's just a spin, right? This is the square of the spin, this is the projection of the spin along the z direction, right? And these 2 wave functions have to satisfy these eigenvalue problems by definition. Perhaps the most straightforward and simplest explanation for spin and the consequences that it brought about was that it required us to rethink the energy levels for the hydrogen atom, okay? So I'd like to go through that real quick just to make sure that the implications are reasonably well understood. Here I've got the quantized energy levels that come out of Schrödinger's equation. These quantized energy levels are specified by the quantum numbers n equals 1, n equals 2, n equals 3, and so on and so forth. Right? Now what we have to add to that is we have to allow for the electron state to be either spin up or spin down. And that just simply means that There's two possible states for the ground state electron in hydrogen. One is a spin-up electron, the other is a spin-down. So this state, which normally just had a degeneracy of equal to 1, this state now has a degeneracy of 2 because there's two possible states, spin-up state, spin-down state. Same thing happens for the n equals 2 quantum state in hydrogen. Originally that had a degeneracy of 4, but that is now changed because the electron can be either in the spin-up or the spin-down state. So for each set of quantum numbers that we've discussed in the previous lectures, those quantum numbers now have to be doubled by including either spin-up or spin-down electrons. And so these original 4 quantum states now go into 8, right? There's now 8 possible ways you can put an electron in the n equals 2 level. So one of the important consequences here is that the degeneracy of the hydrogen energy levels has to include this additional factor of 2 in front of n squared, and that factor of 2 is solely due to the spin of the electron. I'll also say that there's another way to label these states which take into account the fact that the spin is being included, and this alternative way of labeling the states is referred to as term symbols. I just mention the word right now. We're not going to go into detail of how these term symbols are arrived at, but basically there's a term symbol that allows you to classify the symmetry of these different wave functions in terms of their quantum numbers, right? So it's useful to discuss the n equals 2 state just in passing, right? Because you can take the n equals 2, L equals 0, m sub L equals 0, spin up and spin down states, and that gives rise to a term symbol that's referred to as 2s sub 1/2. If you take into account the L equals 1 quantum numbers, that gives you another term symbol which is referred to as the 2p 1/2 set of states. And then there's also 4 additional states that are related to m sub L, to allowed values of m sub L, right? So those 4 states are labeled here in magenta, and that gives rise to another term symbol that's related to those 4 states. So the entire nomenclature for the hydrogen atom is changed because of these quantum spins that have been discovered. Perhaps the most useful and straightforward application of these electron spins is now a really thorough understanding of why the atoms in the periodic table are arranged like they are. So we can now start to appreciate, for instance, the ordering of these atoms and why chemically they all atoms in a given column are chemically similar. I just start to go through that in this slide, just the first few elements in the periodic table. Hydrogen is, of course, the element that we've discussed extensively. The new thing that's been introduced by the electron spin is that now there are 2 states available for an electron in the 1s energy level. When you go from hydrogen to helium, it turns out that one of the states in the 1s energy level holds a spin-up electron. The other energy level in the 1s state holds a spin-down electron, right? So to go from hydrogen to helium, you basically fill up the spin-up and spin-down states in the 1s energy level. When you go from helium to lithium, lithium has 3 protons, it's got 3 electrons, so we have to somehow incorporate those 3 electrons in this energy scheme. 2 of the electrons go into the 1s state. One is spin up, the other is spin down. The 3rd electron can go into the 2s state, and that 3rd electron can either have a spin up or a spin down component associated with it. If we skip a few elements, go to carbon. Carbon's a very important element on Earth. Carbon has 6 protons. It's got 6 electrons, so that means we've got to fill these allowed energy states in terms of spin up and spin down electrons. The 1s state in carbon has a spin up, has both a spin up and a spin down electron in it. The 2s state has both spin up and spin down electrons. And then the 2p state, which is the next state, now there are 6 possible energy levels. The carbon atom has a spin up and a spin down electron in 2 of those 6 energy levels. So the way these energy states fill up, of course, just follows the ordering of the elements in the periodic table, right? And this fact that we've got two columns of elements here, right? That's related to the fact that we're filling up s levels with 2 electrons. The fact that we've got 6, right? We've got 6 elements here, right? That's related to the fact that we're filling up, right, the 6 p levels, right? So these p levels repeat, right? The 2p, there's a 3p, there's the 4p, right? Those energy levels are just associated with the different rows in the periodic table. So finally, with this this discovery of spin, right, the ordering of the elements in the periodic table became completely understood, and that was a real nice advance. Of course, the other problem is why do electron states fill like this? I mean, why are there 2 in the 1s, 2 in the 2s, 2 in the 2p for carbon, right? Why don't all these electron states condense into the lowest energy state, given, and assume a configuration that I've got drawn here? So this is forbidden, and this is experimentally what's observed. Why one, not the other, right? And the answer to that puzzle was provided by Pauli in 1925, where he said, "Oh, there's clearly an exclusion principle that's operating here," and he just hypothesized that there's no that no 2 electrons in a quantum system can occupy the same quantum state. And so the quantum state is defined by the quantum numbers of that state, and that just simply means that no 2 electrons in a quantum system can have the exact same quantum numbers. And that's what would have to happen, for instance, if you tried to jam 6 electrons into this 1s state. You'd end up with the first 2 electrons would have different quantum numbers, but then the remaining 4 would have quantum numbers that exactly match the first 2. And Pauli says that's a forbidden situation. And that just simply means that you have to go to this type of configuration. So we'll explore the consequences of that in a little bit more detail in the next lecture. But at its simplest statement, right, as I can state it as simply as possible, right, this is forbidden because these electron states have same quantum numbers. That's forbidden by Pauli's exclusion principle. This is allowed because these electrons all have different quantum numbers, and that's allowed by the exclusion principle. So we'll try to provide some physical insight into why this exclusion principle exists. That'll come in the next few sets of lectures. The other thing I wanted to end this lecture with was discussion of the spin-flip transition in atomic hydrogen. This is a really interesting topic, and it's basically related to the fact that if in a hydrogen atom, if you've got an electron with spin up executing a motion around the nucleus of the hydrogen atom, that's going to have a higher energy state than an electron with spin down. It's also executing the same motion in the hydrogen atom. So there's a very tiny energy splitting between this spin up and spin down form of hydrogen. And the question, of course, always comes up, why is that so? And you can sort of understand it by just thinking about two bar magnets, right? One bar magnet has got a north pole associated with it. The other's got a south pole associated with it, right? We'll pretend that one bar magnet represents the spin of the magnetic moment produced by this bar magnet represents the spin of the electron. The magnetic moment produced by this bar magnet represents the orbital magnetic moment of the electron. And when you bring the electron, when you confine the electron to one of these quantum orbits, there's an interaction between the orbital magnetic moment and the spin magnetic moment. And if the spin magnetic moment points in the opposite direction to the orbital magnetic moment, right, it's an attractive interaction, right? The orbiting electron actually goes into a lower state, energy state, and that's represented by this picture. If, on the other hand, we take the electron and we flip its spin, and we try to bring it close to the orbital magnetic moment, there's a strong repulsion. I mean, I have to push very hard in order to bring these two things this close together. That repulsion is, of course, indicative of a higher energy state, right? And that represents this configuration. So these simple bar magnets give you some insight into why there's an energy splitting between a spin-up electron and a spin-down electron orbiting the proton in the ground state of the hydrogen atom. This splitting is referred to as the hyperfine splitting, and it was actually predicted in 1944 by von der Hoist, and a lot of experimentalists tried to observe that splitting. It was first measured in 1951 by two physicists from Harvard, Ewan and Purcell. What they found was the radiation that's emitted when an electron goes from the spin-up state to the spin-down state. That radiation was emitted at a wavelength of about 21 centimeters. The frequency that's associated with that transition is in the gigahertz. It's a microwave region of the electromagnetic spectrum. It's about 1.4 gigahertz, right? And that corresponds to an energy splitting that's only like 5.9 times 10 to the minus 6 eV. So the energy splitting is extremely small, right? It's very minute, but it can be calculated based on these interaction energies between the spin-up electron interacting with the orbital magnetic moment that's produced by the electron in motion around the proton, and the spin-down electron interacting with that same orbital magnetic moment. So this was a really important experiment because it confirmed this spin-up to spin-down transition. These energy levels can be calculated with advanced quantum mechanics, so it really gave a lot of confidence that these very tiny energy splittings could be reproduced within the theory. I guess the thing that I find interesting is the whole experiment was done for about $500. So it was sort of a sidebar experiment that was performed. It became very famous, and it actually opened up the field of radio astronomy, because if you look into outer space, there's hydrogen atoms everywhere, and those hydrogen atoms are constantly undergoing this spin-up to spin-down transition, right? Every time they execute this transition, this 21 centimeter radiation line is emitted. So by mapping out the orientation of that, by mapping out the intensity of the radiation that's emitted at 21 centimeters, you're sort of mapping out the distribution of hydrogen in, let's say, galaxies or different interstellar regions of space. So, very famous experiment, and I guess the reason I mention it is because Purcell actually got a bachelor's degree in electrical engineering from Purdue. So he went through a lot of the courses and curriculum that you're going through while you're here at Purdue for your 4 years. So I think that's all I want to say in this lecture. The next lecture I want to focus on the implications of Pauli's exclusion principle. These implications are not obvious. But I'll try and explain it as best I can, and it'll try to provide some fundamental motivation for why two electrons cannot exist in the same quantum state. So please come on back and listen to that. Thank you.